Hi everybody, welcome back to my channel. It's been a few years since I uploaded any videos due to other commitments, and my time's still pretty constrained, so I wouldn't expect a regular upload schedule anytime soon. But I did want to come and just put up a few videos around pwn challenges and buffer overflows, and particularly using pwntools to try and automate exploitation. So this is just something I've been doing a little bit in my spare time recently, and as it's something as quite often happens, I'll spend my time on a certain area and then maybe move on to something else, particularly with academic requirements, without leaving myself any real structured notes or videos and things like that that I can come back to. So this series is more than anything just for myself. I won't be preparing each video in detail. I won't be putting a lot of time into preparation, which might come across in the videos. But if they provide any assistance to anybody else, then that's a bonus, I guess. So the first series that I'll be going through is the ROP Emporium challenges. So there are 8 challenges that focus on ROP techniques. So we'll be going through the 32 and 64-bit binaries in each of these challenges, solving them manually and then solving them using pwntools, and trying to explore some different features of pwntools that can improve automation and things that I might typically not use. So we'll try to, in each challenge, use like a different function or a different technique that I might not have come across before. All the scripts and all the files and things like that will be put up onto my GitHub, which will be linked in the description, as along with obviously the ROP Emporium link here. I would advise, before going through, to go and have a look through the beginner's guide here. It'll explain a bit of stuff which I'm not going to cover in detail, and it'll also just make sure you have any libraries and stuff installed that you need, maybe for dealing with different architectures and stuff like that. So have a look through that. Make sure that you have pwntools installed, so you can get this from GitHub for the latest version. You can install it using pip install. It's just a Python library. And finally, the other thing is GDB. So we'll be using GDB, a debugger in Linux, throughout this, but there are plugins which can be used to help with buffer overflows and reverse engineering, like pwndbg, Jeff, and peda. Now, I would recommend installing this from this GitHub repo, which will install all 3 of these plugins and allow you to just open up whichever one you choose. So if you type in GDB peda, we can boot that. Similarly, if we do GDB Jeff, and they all just load. You can also just run GDB and then init, say peda, and there we go. The reason I think it's good to have these is there are a lot of different features. I mean, peda's no longer maintained, but there are a lot of features in pwndbg and Jeff which each have their own advantages and disadvantages. Because they're actively maintained and have a lot of support for using with different disassemblers and debuggers and things like that, they can prove very useful. The reason why peda is sometimes useful, I think, is its pattern searching functionality, which isn't really matched on the other 2 plugins, and I'll just give a quick demonstration of that to show what I mean. I mean, it's not a big deal, and it's not a reason that I would typically use peda over pwndbg. But I'll just give an example. We have a simple buffer overflow here. Returned a win. So the buffer overflow, we overflow a name field. I can't actually remember how long it needs to be. We overflow the name field, and we want to return to a function. If we do object dump here, let's have a look at it. I'm just going to grep this out. There's a function called hacked, which is where we want to return to. But let's not worry too much about that. This is just for the demonstration purposes. If we do this in pwndbg and we want to find out how many bytes do we need to write into the buffer to overflow it and overwrite the return address, which we'll want to replace with this hacked function. If we were doing this in pwndbg, we would need to create a cyclic pattern, and we can say, let's say cyclic 100. It'll create us this pattern, and we can run the application. Select the file first. We run the application and we paste in that pattern, and we can see it's crashed the application, and because we're using this plugin, it's given us a nice representation of the stack and the registers. And what we want to find out is how many characters did we write into the buffer before we overwrote the instruction pointer. To do that, we take the value that's in the instruction pointer and we do cyclic -L or -O to search, and then we'll get this 28 bytes. So the 28 bytes until we overwrote the instruction pointer. Typically what we might do now is go and just to visualize that, we might just in Python say, let's print out A times 28 plus B times 4 plus C times 32. So we just want to verify this again in a way that's a bit easier on the eyes, a bit easier to see. If we run that, we can see, okay, we had all of our A's, they've overflown the registers, and then right up to our B's, which have overwritten the return address, and then our stack is filled with the C's, which would normally be our shellcode. So that's all good. The thing there was that if we wanted to find out the offset of the EIP, we had to manually take this value and search for it. So we'd have to do similar for any register or any part of the stack we want to find out the offset of. The reason that peda is nice is because we can use a pattern search functionality. So if I run here, return to win, and what we'll do is pattern create. We'll do the same, 100. Take this pattern and copy it. And if we run the application, paste that in, again, it crashes it. It gives us a slightly different representation of the stack and the registers. But rather than now taking this and searching specifically for the offset of the EIP, all we have to do is run pattern search. And this will tell us the offset of the instruction pointer was 28, like it was in pwndbg, but it also tells us, look, this is the offset of the EBP, this is the offset of the EBX, this is the offset of the ESP, and there was 68 bytes on the stack that you could have written your shellcode to, etc. So it just, rather than having to find the offsets manually there, I think that's a nice way to do it. Having said that, the benefits of using pwndbg or Jeff over peda will typically outweigh that pattern search functionality. Okay, so I just wanted to run through that briefly. We're going to start off on the first video going through the return to win binaries in 32-bit and 64-bit. So if you want to make sure you have all the libraries that we need installed, we'll move on to that.